Is a BSc LES stream with a focus on the life and environmental sciences with subjects such as geography, genetics, botany, hydrology, zoology, ecology, and microbiology. In agriculture, there are various different options that involve practical and scientific applications. Students can combine science subjects with specific agricultural disciplines for a 4-year Bachelor of Science in Agriculture degree. These are more career-orientated. Agriculture and agricultural management are 3-year degrees with a higher practical component. Dietetics is a professional qualification that deals with the role nutrition plays in the promotion of health and the treatment of disease. Most degree programs across the college have field trips and projects that contribute significantly to the curriculum. This ensures that students learn in real-life situations under full field conditions. Many of our lecturers have received Excellence in Teaching awards, are recognized internationally, and are rich in practical experience. Students have access to excellent facilities that rank amongst the best in the world. 300 million rands has recently been invested in new teaching and research facilities, state-of-the-art laboratories, and improved equipment. The 30 million rands new School of Engineering building is the envy of engineering campuses across the country. Agricultural students have access to a 356-hectare research and training farm situated near the Pietermaritzburg campus. This facility provides students with hands-on training and is used extensively as an outdoor laboratory for teaching and research in areas such as animal and poultry science, horticultural science, and agricultural engineering. Adjoining Ukulinga is the Bisley Valley Nature Reserve, which supports a diversity of plant and bird species, as well as some large mammals. It provides a rich learning and research environment for staff and students. Based on the Westville campus, the college possesses unique facilities for research into higher voltage power transmission. These facilities are available in only 3 other places in the world and form part of the ESCOM-sponsored Science and Technology Innovation Park. The Science and Technology Education Center showcases the college's scientific achievements and promotes the public understanding of science, engineering, and technology within the region. The college houses a wide range of sophisticated equipment in its microscopy and microanalysis units, staffed by highly qualified and skilled technical specialists. The College of Agriculture, Engineering, and Science prides itself on its graduates who are highly sought after. In a market characterized by a shortage of qualified professionals in science and technology, our graduates are readily employed around the world in the fields of agriculture, science, commerce, industry, engineering, and research, to name just a few. Research plays a major role within the college and operates at the cutting edge of technology. The college has the highest research output in the university and produces the most research publications. There are over 60 well-established research groups and centers within the college. The African Center for Crop Improvement caters for students from all over Africa. It is one of only 2 African plant breeding programs on the continent. Based in the School of Agricultural, Earth and Environmental Sciences, the African Center for Food Security focuses on alleviating hunger in Africa. It offers food security training programs, undertakes academic and applied research, and provides policy and program support. Promoting sustainable engineering practice is the Center for Research in Environmental, Coastal and Hydrological Engineering, or CRESH. It deals with the interaction between engineering and the natural environment. The Mechatronics and Robotics Research Group in the School of Engineering provides an excellent research and education environment for its senior undergraduate and postgraduate students. Judged one of the best research centers at the university, the Center for Plant Growth and Development focuses on high-quality research in the plant-based disciplines of plant physiology, plant molecular biology, and ethnobotany. The Center for Quantum Technology deals with physical phenomena at the microscopic level. Quantum physics led to the development of the transistor and the laser, and is currently being used to develop quantum computers and quantum cryptography. The college is committed to access and readdressing the disadvantages and inequities of the past. The highly successful Unite Engineering program and the Science Access Foundation and augmented programs offer alternative access to university, equipping students from disadvantaged backgrounds with the skills and knowledge to pursue their degrees of choice. Both these programs contribute significantly to advancing Black African scientists and engineers in South Africa. Staff and students contribute to a number of outreach and community initiatives that focus on social responsibility, sustainable development, and upliftment of the wider community. The college also engages in activities involving the pursuit and understanding of science, engineering, and technology through exhibitions, festivals, and roadshows that target high school learners and the general public. The college has minimum entry requirements for its programs. These differ from degree to degree, but all require a national senior certificate and minimum performance levels in mathematics and either physical or life or agricultural sciences. For those who do not meet the minimum requirements, access programs are available. Additional information and brochures can be obtained from the contact information accompanying this video. The College of Agriculture, Engineering and Science is proud of its contribution to the university, the region and the country.
UKZN is one of the best. I definitely understand it's one of the best in South Africa. So for me, there was no other institute that I would have preferred other than UKZN.
With the best.
Okay, good evening, everyone, and welcome back to the second session of our physics revision. Today, we're going to continue with revising the November 2020 paper. So we're going to just carry on now with the last question that we were doing yesterday. I'm sorry. Okay, so this is the question we were doing yesterday. Okay, question 6. And can I just... Okay, just give me one moment, please. Okay, sorry about that. Okay, so this is the question we were working on, a question on Doppler effect. Okay, so just to remind us, let's just start again. The siren of a train moving at a constant speed along a straight horizontal track emits sound with a constant frequency. A detector placed next to the track records the frequency of the sound waves. The results obtained are as shown in the graph below. Okay, and if we look at the graph, we can see that there's a high frequency of 3148, and then there is a lower frequency of 2073. And initially, you have the high frequency, and then at some time T1, the frequency drops to 2073. The first question was, state the Doppler effect in words. And we did that. Let's find question 6. Okay. So it said the apparent change in the observed frequency as a result of the relative motion between the source and an observer. Okay, so that was the definition. Question 6.2 said, does the detector record the frequency 3148 Hertz
So this is of because I'm 7 minutes. Okay, I don't know what's going on now.
Okay, just be patient. The teacher is joining again. I think the network has gone down.
activity problems? Okay, can you hear me and see my screen now?
We can hear you.
Okay.
Your screen has started sharing.
Oh, is it fine now? You can see it.
No, it's not fine. It's in the
It's
process.
not, oh, okay.
We can't see anything.
Is it fine now?
No.
No.
Okay, let me just stop sharing. Okay, is that better?
We can see it now.
Okay, thank you. Moves towards the detector or away from the detector. So we can see that 3148 is frequency, which means that the train is moving towards the detector. Okay. 6.3. The speed of the train take the speed of sound in as 340 meters per second.
Ashila, we don't have sound for you. I think the connectivity is very bad.
Okay, so this is what we'll do. We have to write down the equation for finding the frequency. So the Doppler equation. I'm just going to highlight it now because we. Yes. Yes.
Okay, there's clearly a problem on the teacher side, right? So there's some connectivity issues. Can you just bear with us for 1 minute? Maybe you can switch network and we'll try to get a more stable connection. Thank you.
Okay, I'm back now. Sorry about that. Can you hear me and can you see my screen?
Yes.
Okay, thank you. Okay, so this is where we are. We're trying to find the speed of the train and taking the speed of sound in air as 340 degrees. So what we're going to do now is to write two equations because we don't know what the frequency of the source is. Okay, so we will write out the first equation. The frequency that the listener hears is V plus, and then the speed of the listener. So the listener in this case is the detector, and the detector is fixed, so it has no speed, so that is 0. And in the denominator, we have V, and it's either plus or minus the speed of the source. And then we know that the source is moving towards the detector, so it's a negative sign. Okay, so we can rewrite the equation as FL is equal to V over V minus Vs times Fs. And then the other equation we can write is for the lower frequency when the train is moving away from the detector. So if it's moving away from the detector, then the sign in the denominator becomes plus. Again, the speed of the listener is 0. So if we rewrite the equation here, we can compare these two and we can write them out in terms of Fs. This Fs, the frequency of the source, is exactly the same. So we now can equate these two, the two equations that we have. Okay, so this is where we were yesterday. So now you can see that this is equal to that. And we can solve for Vs. Okay. So what we'll get is 3148, because it's just the maths now. You're going to take 3148 times 340 divided by 340, and then 3148 times minus Vs over 340. And when you do this, then you're going to get 3148 minus 9.26 Vs, and that's equal to, 2073 plus 6.10 Vs. Okay, and this is just the maths now, once you've equated these two red blocks. And if you solve this, then you get that Vs is equal to 69.99 meters per second. Okay, so that is the speed of the train. So we can just call it 70 meters per second. So that is the method you use to calculate the speed of the train when they did not tell us what the frequency was. Okay. Okay, so now we want to, the next question is, the detector started recording the frequency of the moving train siren when the train was 350 meters away. Sorry. Okay, so what we know is delta X is equal to 350 meters. They want us to calculate what the time was, so we're trying to find delta T. And we know that the speed of the train is 70 meters per second, or you can just write it as 69.99. Okay, so let me just get back to the paper. Okay, so remember the detector started recording when the siren was 350 meters away. And what is the time T1? So it means that here at time T equal to 0, the train was 350 meters away. And so from 0 to T1, it traveled 350 meters and the speed was 69.99 meters per second. So can you calculate the time? If you know the distance it covered and you know the speed that it was traveling, can you find the time? Yes, you can. Okay, so we know that speed is equal to the distance covered over the time taken. So if we want to calculate the time, then the time is just delta x over v, which is 350 divided by 70, or 69.99. And if you do that, you should get 5 seconds. Okay, so on the graph, here T1 is 5 seconds. Okay, so that is how we answer that question. Do you want to ask me anything? Do you have any questions on the solution that we did? Okay, if there's no question, we'll move on to the next one. Okay, question 7 says, 2 small charge spheres, A and B, placed on insulating stands 0.2 meters apart, as shown in the diagram below. They carry a charge of -4 × 10 to the -6 coulombs and +3 × 10 to the -6 coulombs, respectively. M is a point that is a distance of 0.1 meters to the right of sphere B. And the first question, 7.1, is calculate the number of electrons in excess on sphere A. Okay, so when they want us to calculate the number of excess electrons, that is straightforward, just using the equation for that. So question 7.1, the number of electrons that's in excess is equal to the charge divided by the charge on an electron. Okay, and what is the charge of A, on sphere A? It is -4 × 10 to the -6 coulombs divided by, and what is the charge on an electron? Okay, so you look at your information at the back of your question paper, and it's got all the constants there. And then you'll see that the charge on the electron is -1.6 × 10 to the -19 coulomb. And so you can see coulomb cancelled with coulomb, so there is no unit in your answer. It's just a number, and the answer is 2.5 × 10 to the 13. Okay, that's how many excess electrons were on sphere A. Okay, 7.2, calculate the magnitude of the electrostatic force exerted by sphere A on sphere B. Okay, so you have the 2 spheres. What is the electrostatic force that A exerts on B? Okay, so even this one, I think you'll be happy to do. So 7.2, so the force that A exerts on B is equal to, it's Coulomb's law, K Q1 Q2 divided by R squared. Okay, and whenever you substitute into this equation, everything must be in SI units, right? So your charge must be in coulombs, not nanocoulombs or microcoulombs, and the radius or the distance between it must be in meters. Okay, so then substitute the values. K is a constant. You'll get the value from your table of constants. Q1 is 4 × 10 to the -6, and Q2 is 3 × 10 to the -6. The radius, the distance between them is 0.2 meters. Squared. Okay, so what you see here is they told us that the charge on A is -4 × 10⁻⁶ coulombs. But when I put it into the equation here, I did not put in the minus sign. Okay, so when we're doing these calculations, we're finding the magnitude, you do not put in the signs of the charges. Okay, you only put in the magnitudes, because to the sign, when we calculate our answer, we will know what the direction is. Okay, and I'll show you that just now. So if you put this into your calculator, you get 2.7 newtons. Okay, so that is the force that A exerts on B, 2.7 newtons, okay? So let's go back to the question. So here it is. Calculate the magnitude of the electrostatic force exerted by A on B. And we worked it out now as 2.7 newtons. What is the direction of that force? What is the direction of the force that A exerts on B? Okay, so to answer that, we have to look at what the charges are. So A is a negative charge and B is a positive charge. So these are unlike charges. They're different. And so they are going to attract each other. So A is a negative charge, B is a positive charge. A is going to attract B to itself. So that is the direction of the force. The force we calculated now that A exerts on B, it's 2.7 Newton and its direction is to the left. Okay. What if I had to ask you, now, what is the magnitude of the electrostatic force exerted by sphere B on sphere A? Then what would the answer be? Okay, we wouldn't have to go and do a whole calculation, because if A exerts a force on B, then from Newton's third law, B is going to exert a force on A that will have the same magnitude, but the opposite direction. Okay, so that's just to remind you about finding the force that one sphere exerts on the other. And when you're putting it into the equation, do not put in the signs. Okay, so the next question is, describe the term electric field. Okay, so what is an electric field? How do we know if an electric field exists anywhere? Okay, so the way to do it is, if you have a region or a space and you want to know if an electric field exists in that area, you take a charged particle and put it there. If the charged particle experiences a force, then it means there's an electric field present. So an electric field is a region or a space where an electric charge experiences an electric force. Okay, so when you're writing out these definitions, you must write in electric charge and electric force instead of just saying charge and force. Okay. Okay, the next question is, calculate the magnitude of the net electric field at point M. Okay, and that's for 5 marks. So here's point M, and they want you to calculate the net electric field here. So you have charge A, which is a negative charge, and sphere A is going to have an electric field here at M. And B, the charge B here is also going to have an electric field at M. So we want to know what is the net electric field in that area. Sorry. So the way to do it is, first find out what is the electric field at M due to A, and then calculate electric field at M due to B, and then add it up. Okay, so that's the way to do it. So that's what we're going to do now. To do that, we need to know what the charge is. We know that A is -4 and the distance from A to M. So from A to B is 0.2 meters. From B to M is 0.1. So the distance from A to M is 0.2 plus 0.1, which is 0.3. Okay, so let's do that. So 7.4. So the electric field due to A at M is equal to KQ over R squared. Okay, substitute the values here. 9 times 10 to the 9. And Q is -4 times 10 to the -6. Again, we do not put in the sign of the charge. You just put in the magnitude. And the radius is 0.3 meters squared. Okay, and then the answer that you get is 4.0 times 10 to the 5. So if you have your calculators, you should be checking out these, all of these and putting the values in and checking the answers. Okay, and then it is Newton per Coulomb. And then what is the direction of this electric field? This electric force that A exerts at M. What is the direction of it? If A is a negative charge. If A is a negative charge, then electric field lines go into, oops, a bit of, okay, so the electric field lines go into the negative charge, which means the electric field there is going to be in that direction, to the left. B is a positive charge. So how do the electric field lines go from positive charges? They go outwards. Okay, so the electric field lines go out of the positive charge. So at M, the electric field due to B is going to be to the right. Okay, so here, and it is to the left. Okay, so let's do the same thing now for the electric field that B exerts at M. It's KQ over R squared, 9 times 10 to the 9, and Q is 3 times 10 to the -6. Yeah. And the distance is 0.1 squared. Okay, if you do that, you get 2.7 times 10 to the 6 newtons per coulomb, and the direction is to the right. Okay, so we know what the field is due to A, we know what the field is due to B, so we can calculate the net electric field. At M. Okay, so the net electric field is equal to electric field of A plus the electric field of B. Now, when we're doing this, we have to know that one of the fields is to the left and the other is to the right. So we must choose a direction that we're taking to be positive. So I'm going to say that to the right is positive. Okay. I'm taking it to the right to be positive. Then electric field due to A is going to be minus 4.0 times 10 to the 5 plus the field due to B is positive because it's pointing to the right 2 times 10 to the 6. And if you add that up, you get 2.3 times 10 to the 5 newtons per coulomb. And it's positive, which means that it is to the right. And that is how you calculate the net electric field at M. Okay, so that was for 5 marks. You had to do all of those steps. Okay, are you happy with that? Do you have any question?
Ursula,
Yes.
one question in the chat. The student is just checking on the direction of the electric field. Is it out of the positive charge and in towards the negative charge? The student is just checking on the direction of the electric field. Is it always
okay.
out of the positive charge and into the negative charge?
Yes, yes, that's correct. Okay. So yes, this is the rule. So wherever you have, wherever we have a positive charge, then the electric field lines are going to go out of that charge. Oops. So it always goes out. That's a rule. Okay. So if you have a positive charge, the electric field lines go radially out of it. And if you have a negative charge, the electric field lines go radially in, always. That's how we know the direction.
Okay, thank you.
Okay, are there any other questions?
There's a couple
Okay.
more on the chat. If you
Okay.
could, you know. So the student wants to know to explain to them why you used 0.3 for R.
Okay, that's the first one. So let me just erase all of this. So the equation is, and I'm just going to show you this again here. It's the equation is E is equal to KQ over R squared. Okay, and R is the distance from A. So I have my eraser on. R is the distance from A. Oops, to M. That's the distance. We want, this is R. Okay, so the distance from A to B is 0.2 meters. That will only take us here. And then from the rest of it, it's 0.1. So R for A is equal to 0.2 plus 0.1. And that's why the radius is 0.3. Okay.
Okay, thank you.
Are there other questions? Okay, so here's one that's a little bit of an application or some understanding. They tell you now these charged spheres, A and B, and another sphere D are arranged as they show us in this diagram. Okay, so this along the X and Y axes. And then they tell us the distance between A and B. Well, we know it's the same ones from the top here, okay? We've just added a third charge D into here. And they tell us that the net electrostatic force experienced by A is 7.69 newtons in the direction as shown here. Okay, so when we're looking at this, we know that force is a vector, and we remember some of our vector notes. The question is the charge on sphere D positive or negative? Okay, so how will we know if it is positive or negative? So the first thing that we'll do is, if this is the force, okay, this is the force here, then that force, I'm just going to draw it out here so that I can make a mess. If that's the force 7.69 newtons, then that force will have an X component in that direction, and it will have a Y component there. Okay, that's what we need to realize. So you had a force pulling it in that direction here, which we call this X here, and we've got one there. So this one at the bottom here is due to B. Okay, and that is B exerting a force on A, pulling A towards B. And then what is this line here? That is due to the charge D. And what is D doing? D is pulling the charge up. Okay, so just by looking at the drawing here, by us drawing this, components of the vector that was given to us, so I could even put it right here, X and Y, I can see that D is attracting A. And we know that A is a negative charge. Okay, and B is attracting A, which means that B is a positive charge. That's how it will get pulled in that direction. Now, if they are telling us that A is being pulled upwards, what will the charge be on D? It has to be positive because it's attracting A. If it was negative, then the force would be pushing A down, pushing it away. Okay, so because the force is upwards, and we know that by looking at the 7.69 vector, if we're looking there, we know that this has to be a positive charge. Okay, so the answer to 7.5 is that it is positive. Okay. And then the next one, there's only 3 marks, but they want you to calculate the magnitude of the charge on D. Okay, what is the charge on D? How are you going to do that? How can you find the charge? So what do we know? We know that the resultant or the net force is 7.69. And we know the force between A and B because we just calculated that. So can you see that we're going to use vectors now? We already know. So if I can draw this out here for you, that's 7.69 newtons. And then here is FAB, which we know. And the one up there is FAD. And that's what we can find. If we can find the force between these two, then we can calculate the charge. Okay, so that is what we're going to do now. But you need to understand the reason we did that is they gave us 7.69, and we can see it from theorem of Pythagoras here, and we'll be able to find the force between A and D. Okay, so that's what we'll do now. Okay, so I'm going to say that the net force squared is equal to force on AB squared plus the force AD squared. Okay, and now this force, the net force is what we're trying to find. So we're trying to find FAD. And that is equal to the square root of F net squared minus FAB squared. Okay, so I just did 2 steps in here. I'm sure that you can follow it. I just made FAD the subject. So that one went over and took the square root. Okay, so that is the square root of what is F net? They gave it to us, it was 7.69. And what is FAB? That we calculated here. Okay, 7.1. So this one. So minus 2.7 squared. Take the square root of that, and we get 7.2 newtons. So that is the force that A exerts on D or D exerts on A. Okay, the magnitude is the same. The question was, what is the charge on sphere D? Calculate the magnitude of the charge. So if you know what the electrostatic force is, and you know the one charge, you know the distance between them, can you find the other charge? Yes, you can. And you're going to just rearrange Coulomb's equation. Okay, so you've got K, Q1, Q2. And if you want, we can call it QA and QD, but we leave it as 1 and 2 divided by R squared. Okay, so I'm trying to find Q2. So I like to rewrite the equation as Q2 is equal to, so we're going to multiply both sides by R squared. So I'm going to have F times R squared. And then I'm going to have to divide both sides by KQ1. Okay. Okay, I'm sure you know how to do that. Okay, so now we just substitute all the values. So what is F? We just calculated it, it's 7.2. So 7.2. And what is R? R is 0.15. 0.15 squared divided by K is the constant, 9 times 10 to the 9. Q1 is the charge on A, which we know now is 4 times 10 to the minus 6. Okay. So put all that into your calculator and you get 4.5 times 10 to the minus 6 Coulomb. Okay, and we already know that it's positive, but they asked for the magnitude only. So 4.5 times 10 to the minus 6 Coulomb. That is the charge on sphere D. Okay, that was the last question for question 7. Are you happy with that? Would you like to ask any questions?
A student is asking about a direction. Sorry, Ashley.
Yes, I can hear you.
The thing is, a student asking, how do you determine a direction? In this case, I don't think you do need it, but you may answer that, I think.
Okay, so for Q2, it's only the charge, right? So I'm assuming if you're asking about the direction, are you asking about the direction here? Okay, so if we want to know about the direction of the forces, if that's what you're asking, then that just depends on what your charges are. So I'm just going to make a little space here. So if you have a positive charge and you have a negative charge, then you know that the negative charge is going to pull the positive charge in that direction. So if I call this, oh, I should just write it the other way, according to how our charges are. That's the negative charge and that's the positive charge. And this is A and B. So if we look in here, then B is going to pull A. Okay, so the force that B exerts on A is to the right. What is the direction of the force that A exerts on B? So A is going to pull B. So A is going to exert a force to the left. If I have another charge, now I'm going to put it up here, another charge there, and this charge is positive, then what is going to be the direction of the force that the new charge is going to have on A? Because it's a positive charge, it's going to pull A upwards. So that's how I know what the direction is. It depends on what the charge is. In this case, they told us this is the direction here of the net force. The net force is like that. So if your net force is like that, then your components will be there and there. And just one other example, if they told us that the net force was like that, then our components would be in that direction. Oh, sorry. If this was my net force, then my component would be in that direction, but in the y direction, it would be down. Okay, so I'm using theorem of Pythagoras or my vector rules there, and knowing whether it's a positive charge or a negative charge. That will determine the direction. Okay, was there any other question?
No, I think that was all. Thank you.
Okay, so let's move on to the next question. Okay, so question 8. So somebody was asking yesterday about electricity. So here's the question now. A battery with an internal resistance of 0.5 ohms and an unknown EMF, E, is connected to 3 resistors, R1, R2, and R3. A high resistance voltmeter and an ammeter of negligible resistance as shown in the circuit diagram below. Resistance of the connecting wires must be ignored. Okay, so when you have these questions, you must look at the circuit carefully, identify all the resistors, and look for the voltmeter, the ammeter, and in this case, we have a switch as well. Okay, first question, define the term EMF of a battery. What is the electromotive force? Okay, so that's a theory question. And the EMF is just the energy, the total energy that is supplied by the battery per coulomb of charge. Okay, actually, okay, let's. This is question 8.1. Okay, so you can say that, you could also say that it's the work done by the battery to move 1 coulomb of charge across the circuit. Okay, so what's important is the EMF is totally what the battery does. Okay, so I'm just going to write the shorter one, which is the total energy supplied by the battery. Per coulomb of charge. Okay. Across the circuit. Okay, so especially if you write in the matric exam, and they're asking you for definitions and define the terms, write all the important words in, okay? So rather write a little bit more than to write a little bit less. Okay, so the EMF is the total energy supplied by the battery per coulomb of charge across the circuit. Oh no, so it's just, right. It's total energy supplied by the battery per coulomb of charge. Not across the circuit. Okay. And, or you could also say that it is the work that is done by the battery to move 1 coulomb of charge across the circuit, whichever one you choose, right? Okay, here comes the interesting parts now. The reading on the voltmeter decreases by 1.5 volts when S is closed. Okay, and it says, give a reason why the voltmeter reading decreases. So when you're looking here, if you look at the circuit, you can see that this voltmeter is only connected across the battery, which means the voltmeter is reading across the battery. So when you close the switch, then current's going to flow in the circuit. When the switch is open, the voltmeter will still give you a reading. It will read the EMF of this battery. When you close the circuit, when you close the switch, sorry, current is going to flow in the circuit. And they tell you that when you close the switch, then the voltmeter reading decreases by 1.5 volts. Okay, so it means it had some reading when the switch is open, close the switch, and that reading goes down by 1.5 volts. Why does that happen? Give a reason why the voltmeter reading decreases. Do you know why? Okay, we do know why. It's because the energy is lost in the battery due to the internal resistance, okay? So I'm going to say, and how do you even know that the energy is lost? How do we experience this? Energy is lost in the battery. Very often the battery gets warm or it gets hot, and it heats up because energy is being lost through the internal resistance. So in this question, and if you're answering in the exam about this, why does this happen? The most important part is due to the internal resistance. Okay. So even though the battery is supplying some energy to us, it's also using up some of that energy to overcome its own internal resistance. Okay, so energy is lost in the battery due to internal resistance. And then I'm just going to put a little thing here that says heat. It's lost as heat. Heat is lost. Okay. Eight 8.3 is calculate the following when the switch S is closed. What is the reading on the ammeter? Okay, so when you close the switch, what reading will we get on the ammeter? Okay, so we know we're going to be able to do this. We need to know the resistance, or we need to know the potential difference, the voltage. So we haven't yet calculated what the resistance in the circuit is, but what have they told us so far? They've told us that the voltmeter reading decreases by 1.5 volts. And we know that the reason for that was due to this internal resistance. So the voltage used up there was 1.5 volts. And we know that the resistance is 0.5 ohms. Can you calculate the current? You have V and you have R. Can you find I? Okay, yes, you can. So for 8.3, I is equal to V over R. Okay. They told us that it decreased by 1.5 volts, so we know that it's 1.5, and the resistance is 0.5 ohms. And if you put that in your calculator, you get 3 amps. So that was the easy way to calculate the current that is flowing in the circuit. Okay. So when they asked us, what is the reading on the ammeter? That's another way of asking what is the current that's flowing in the circuit. Okay, now, what is the total external resistance of the circuit? Okay, when you get a question like that, you must get it right, because resistors in series and parallel are very simple to solve. Okay, you've got all the equations at the back of your question paper. So we can do this. Total external resistance. So let's look at the circuit. Externally, we have R1, R2, and R3.
Sorry, Ashley. Sorry.
Yes.
There's a student who's asking a question here.
Yes.
He's asking, why do we use ohms, not 4 ohms for resistor?
Okay. So what I'm trying to find here is the current through A. Okay, so to answer that question, what we know is that the voltmeter reading is decreasing by 1.5 volts, okay? The voltmeter reading decreased by 1.5 volts. And I told you before, if you look at this voltmeter, it's only connected across the battery, okay? So it's reading across the battery. So the V changed by 1.5 volts. So I know that V is 1.5. And I know that R here is 0.5. So I know V and I know R. And I'm trying to find I. So that is why I used the values I used. I used 1.5 and 0.5 because 1.5 volts is across there and 0.5 is across there. I can't use 4 volts because I do not know what V is across that resistor.
Okay, thank you. I think it's noted. Thank you.
Okay. Okay, so then now they want us to find the total external resistance in the circuit. So we've got R1 and we've got R2 and R3. So when you look at it now, we can see that R2 and R3 are connected in parallel with each other because you've got the current coming in there and then it has to divide. Some goes through R2 and some goes through R3. So when we want to find the total external resistance, we first find what is the equivalent resistance of R2 and R3, this parallel combination. When we have that, that resistor is connected in series with R1. And so then we'll add R1 to it and we'll have the total external resistance. Okay, so that's what we're going to do now. So R2 is 25 ohms and R3 is 15 ohms. Okay, we need that now.
Just,
So this is,
sorry,
yes,
just one more question again.
yes.
The student is asking which direction is the current. The question
Which
is
direction?
which direction is the current moving?
Okay, so I could hear what direction is the current moving. So the current flows, conventional current flows
So when
from the
you're
positive.
looking at your circuit, in which direction is it flowing towards?
Okay, so here's the battery. You look at the battery, you know that it's got two terminals, the positive and the negative. So the longer terminal is the positive and the shorter one is the negative terminal. And so current always flows from the positive, out of the positive. So it comes out of there all along the circuit like that. It divides there, then it comes back here, flows through the switch and back into the negative. That's the direction. That's the direction of conventional current. It always flows from the positive terminal of the battery all the way through your circuit to the negative terminal. Okay. Okay, so now let's answer finding the total external resistance. So I'm going to find first the parallel combination. Okay, so that's 8.3.2. Okay, so the equation is 1 over R parallel is equal to 1 over R2 plus 1 over R3. And that is equal to 1 over 25 plus 1 over 15. Okay. This is the equation that's given to you. Now, when you get to this stage here, you can solve this however you want to. You can put it directly into your calculators or you can just write it out in a simpler form. So I'm just going to write it out again, right? 1 over RP is equal to that. So then 1 over Rp is equal to, the way to do it is to say it's 25 times 15 over 15 plus 25. And so 1 over R parallel is equal to that. So R parallel is equal to the inverse of this. So it becomes 25 times 15 divided by 15 plus 25. Some of you may already just know the rule and say that it's product over the sum. However you do it, it's fine. And when you put that into your calculator, you get 9.375. Okay, 9.38. And it's a resistance, so it's ohms. So that's what the parallel resistance is, or the resistance of those two, the equivalent resistance of R2 and R3. So the question was, let's go back here, find the total external resistance. So we found R2 and R3. If you look at your circuit, there is also R1 here, which is 4 ohms. So R1 is connected in series with these other two. So if I want to find, I'm calling it R external, I should call it R total. Okay, so R total is equal to, for the external, is going to be R parallel plus 4 ohms. Okay, let me just see what it's called, R1. So let's just call it R1. And so that is equal to 9.38 plus 4 ohms. And that is equal to 13.38 ohms. So that is the total external resistance in the circuit. Okay. And then the last bit of this is, what is the EMF of the battery? Okay, so do you know already? It's an easy equation. 8.3.3. How do we calculate the EMF? It is equal to I R plus little r. Okay, so it's the total current that flows in the circuit multiplied by R. The capital R is the total external resistance, which is why they asked us to calculate it now. Plus this little r is the internal resistance in the battery. Okay, so what is that equal to? So what is I? I was what they asked us to calculate right in the beginning. The question didn't say what is the current, it said, what is the reading on the ammeter? And so we know that the ammeter reads current, so that was I. So I is 3 amps. The total external resistance, we just calculated it as 13.38, plus the internal resistance of the battery was given to us as 0.5 ohms. And if you put that into your calculator, you will get 41.64 volts. That's the EMF. Okay, are you happy with that? Okay. Okay, so there's another part to this. It's 8.4. A learner makes the following statement. The current through resistor R3 is larger than the current. Okay, yes?
Sorry, Ashley.
Okay, I can hear you, but you're breaking up.
Sorry. Can you please re-explain that EMF? I don't think everyone got it. They're trying to actually get it. Can you please re-explain it?
Okay, okay,
I was saying, can you please repeat the last? Can you?
okay.
Yeah, to
Sure.
re-explain
Yeah,
it. I don't think everyone got it. Yes, thank you.
okay. Okay, so they're asking us now. So question 8.3.3 is asking us, what is the EMF of the battery? Okay, so in our circuit here now, this is what they want us to find. What is this value of E? Okay, now the EMF, remember they asked us the first question, define the term EMF. And that is the energy that the battery is supplying to the circuit. The way that we calculate it is just to say that E, which is actually V is equal to IR. Okay, but it's only the V across the battery. So it's the EMF is equal to I times R. But what is R? Okay, so if we look here, we know what I is. I is the current that's flowing here. But R is the total resistance in this whole circuit. So if we look at it, we calculated the resistance here for R2 and R3, that was R parallel. We calculated that. We added that to R1. So we got the total external resistance from the circuit. But there's also this little R here inside the battery. It's called the internal resistance. So when we want to use the equation, V is equal to I times R, we have to take into account R1, R2, R3, plus the internal resistance. And so if we do that, we use this equation here. This equation, E is equal to I into R plus little r. Okay, so that's what this equation is. So I is the current which flows through the circuit, which is 3 amps. We calculated that. And you, in the brackets, you've got capital R. Capital R is the total external resistance in the circuit, which we've calculated here as 13.38. And you must also add the internal resistance of the battery. The internal resistance is 0.5. So that is what we did. We said I into external resistance plus the internal resistance. And if we put that into the equation, we will get the EMF that is supplied by the battery. Okay, is that better?
Yes, thank you. It's clear. Thank you.
Okay. Okay, so now we're talking about 8.4. It says that a learner makes the following statement. The current through resistor R3 is larger than the current through resistor R2. Is the statement correct? Choose from yes or no. So we have to first answer that, and then we must explain the answer. Okay, so what does the learner says? The current through R3 is larger than the current through R2. So when you get a question like that, you come and look at the circuit. Okay, so you can see the current coming into the circuit here from A. Here's the current here. And it's dividing to go into R1, R2 and R3. So how will the current divide? You know that R2 is 25 ohms. And you know that R3 is 15 ohms. So how will the current divide? What do you know about the current when it has to split or divide between resistors? Okay, so what we know is when the current divides, the more current is going to flow through the smaller resistor. Okay, so the current doesn't like to do a lot of work. So if you have two resistors, then in this case, you've got R2, which is bigger than R3 because it's 25 ohms. This is 15. R2 has a higher resistance. Therefore, less current is going to go through there. More current is going to go through R3. And so if we look at what the learner said the current through R3 is larger than R2. Is this correct? Yes, it is. And why? How do you explain our answer? And that's what we'll do now. It's what we just said. Okay. So that is 8.4. So 8.4, choose from yes or no. Is the learner right? Yes. And why? And it's important now when you're answering this question, if it comes out in the exam, you have to first say for the same potential difference. Okay. For the same potential difference. Because that tells us that we're talking about the same situation, right? For the same potential difference, a larger current will flow through a smaller resistor. Or a smaller resistance, right? And that just comes from Ohm's law, from V is equal to IR. So if you have a constant V, so the same potential difference, then if R is bigger, I will be smaller. Okay, so that's how you explain it or how you can remember it. For the constant V, if R is bigger, I is smaller. If R is smaller, I is bigger. Okay, so you must be able to explain it. So the student is right. More current will flow through the smaller resistor. And then for 1 mark now, 8.5, the 4 ohm resistor is now removed from the circuit. Okay, how will this affect the EMF of the battery? Choose from increases, decreases, or remains the same. Okay, so the 4 ohm resistor is now removed. So which is the 4 ohm? So we're here now, this 4 ohm resistor. If we remove it from the circuit, then what's going to happen? Okay, so because it was in series with this whole circuit, it will decrease the total external resistance. Okay, so if you take R1 out, then the total resistance in the circuit will be less, it decreases. But the question asks, how will this affect the EMF of the battery? Now, what is the EMF of the battery? The EMF is the energy that the battery is supplying. So where does it come from? It comes from inside the battery, from whatever chemicals are inside the battery. So the EMF that is supplied by the battery depends on the battery, okay? It has nothing to do with what happens to the 4 ohm resistor. So how does it affect the EMF? Does it increase, decrease, or remain the same? And we know that it remains the same. So that's 8.5. Okay, so removing that does not change. Okay, are you happy with that? Or do you want to ask me any question? No questions?
There is a question, sorry.
Okay.
There's a question here. I think if you can please repeat that explanation, if you can, please. And I think someone raised their hand. I'm not sure if they want to talk. Can you talk? The person who raised their hand, can they talk? the scissors. You may ask the question.
Can you hear me?
Yes, we
Yes,
can
we
hear
can.
you. Thank you.
Okay. At 8.4, I was asking if I can explain as if the current is inversely proportional with the resistance, and the resistor R2 will have a lower resistance as it has a higher, or will have a lower current as it has a higher resistance, and R3 will have a larger current since it has a low resistance. Will be that all right?
Yes, that is perfectly correct. Yes, that is right. It's 100% correct.
Okay, thank you.
Okay. What was the other question, Zwandile?
I think someone was saying, may you repeat the last explanation? I
Oh,
think
yes.
you did.
Oh, okay.
I think the very last
Yes.
explanation you did, they ask if you can please repeat it. Please repeat the last question, they say.
Okay. Okay, so 8.5 was asking if we remove, so the 4 ohm resistor is now removed from the circuit, how will this affect the EMF of the battery? Choose from increases, decreases, or remains the same. Okay, so the EMF of the battery is the energy that the battery is supplying. So if you remove the 4 ohm resistor, it will not change the EMF of the battery. Okay, the EMF of the battery does not depend on what else is connected in the circuit. It only depends on what the size of the battery is. If it's a 24-volt battery, then the EMF is 24 volts. If it's 42 volts, it's 42 volts. Okay, so the EMF is not affected by the 4 ohm resistor or any of the other resistors in the circuit. Okay. Is that fine?
Yes, I think it's clear. Thank you.
Okay, thank you. Question 9. Okay, so a simplified diagram of an electrical machine is shown below. And the first question is this machine a DC motor or a DC generator? Okay, so how do we know if this is a motor or a generator? Okay, so we look at this. And what is that? That is a battery. So because it's connected to a battery, we know that this is a motor. Okay, so let's write down the answer here. It's a DC motor. And then I'm going to write here, because it is connected to a battery. And the next question is, write down the energy conversion that takes place while this machine is in operation. Okay, so it's got a battery here, so we know it's going to change electrical energy. And what does it change it to? Now this is us just knowing about how the motor works. So the answer is electrical energy to mechanical energy, or you could say electrical energy to kinetic energy. Both would be correct. Okay, so electrical energy to mechanical energy. And here I'll just put in brackets kinetic, because you could also say it's electrical to kinetic energy. I'm writing. Write down the name of the component A in the diagram. Okay, so what is A? Do you know what it is? 9.1.3. A is the commutator. Okay, it's a commutator. You could also call it a split ring. Okay, both are acceptable. That's the commutator. And then 9.1.4 is asking us in which direction will the coil rotate? Is it clockwise or anti-clockwise? Now, I don't know how to do this because I wanted to put the video on and show you how to use the left-hand rule. Okay, so just in case we have any problems, I'm going to come back to this. Just remind me. Because I'm not sure about our connectivity now. I'm going to have to, my light is not so good here. Okay, I'm going to come back to 9.1.4 to show you using Fleming's rule, how to put your fingers to find the direction in which the coil is going to turn. Okay, so we're coming back to that one. Let's go on to 9.2. An electrical device is marked 200 watts, 220 volts. Define the term RMS voltage. Okay, so root mean square voltage. I've seen this a few times, so do you know? Okay, so what's this? 9.1.4, I must come back. 9.2, what is that whole story? What is RMS voltage? Okay, I think it would be a good idea if you learn it off, because I've seen that at least twice. So I'm going to write your RMS voltage of AC. It's actually the RMS voltage of AC is the AC voltage which dissipates the same amount of energy as an equivalent DC voltage. Okay, so that's what the RMS is. So it's the equivalent between the AC voltage and the DC. But we have to write it out for marks. So the RMS of AC is the AC voltage which dissipates, which means gives off, the same amount of energy as an equivalent DC voltage. Okay, so the RMS voltage of AC. Oh, I wrote your VRMS. You must write RMS of the RMS voltage of AC is the AC voltage which dissipates the same amount of energy as an equivalent DC voltage. Okay. Calculate the resistance of the device. Okay, so they've given us that it's marked 200 watts, so that's a power, and 220 volts, the potential difference or the voltage rating. Okay, so you've got P and you've got V, and they want you to calculate the resistance. Okay, so that's how you look at what's given to you, and then you choose the equation that is the easiest for you. Okay, so sometimes it might even be worth it to take a few moments to look through your equations, see what's given to you, and see which one is the easiest one to do. So there are, again here, there are many different options that you can use, and I'm going to show you the one that I think is the best. Okay, 9.2.1. 0.2, sorry. So they told us that P is 200 watts and the V is 220 volts. Okay, that's what they gave us. And now we want to find R. So the equation is, and if you look at your equation sheet, it's that the average power is VRMS squared over R. Okay, that's the equation that we should use. We're trying to find R. So R is just V RMS squared divided by P average. And that's equal to 220 squared divided by 200, which gives us 242.
Are you there still? Are you still there? I think we lost her sound a bit. She's coming back, I'm sure.
Yeah, I think the network took her out. Angela,
Yeah, I
a
think
question. When
sorry?
when Angela comes back, maybe the student has a question.
Not yet. No.
There's someone with a hand. Says he's
No, that hand is. Oh, can you please raise down your hand? I see this hand is old. The Sizwe, please raise down your hand. Lower down your hand, please. Okay, thank you.
Ms. Wandile, can you hear me?
Yes, we can hear you now. Thank you.
Okay, so okay, I hope you all saw the last calculation of how we got 242 ohms.
Please, can
Okay,
you
so I'm gonna
re-explain?
continue from.
Can you please re-explain it? I think we lost you there actually when we were trying to explain that.
So 9.2.2, this last one, I must just redo that.
Yes. Just re-explain it quickly, then you can move on, please. Thank you.
Okay, thank you. Okay, so the question there was, an electrical device is marked 200 watts, 220 volts. Then they asked us to define RMS voltage, which we did, and then calculate the resistance of the device. So I was saying to you that when we want to calculate the resistance, so we must write down what's given to us, which in this case is the power is 200 watts and the voltage is 220 volts. So we know that we have P and we have V, and we want to calculate the resistance R. So if you look at the equations, then this one here, the average power is just V RMS squared over R. So if we substitute the values that we have, then we'll get R equal to 242 ohms. Okay, and then the next question now that we want to do, or to answer, it says, This device is now connected to a 150 volt AC source. Calculate the energy dissipated by the device in 10 minutes. Okay, so it's now connected. The new voltage now is 150 volts. What is the energy dissipated in 10 minutes? Okay, so the energy dissipated, we want to know what is this work that's being done here? So that's what we're going to do. Again, there are many choices for the equations that you can use, but let's start by writing down what is given, okay, for this one, for this example. So they told us we now connected to 150 volt supply. We calculated the resistance to be 242 ohms. They told us they want us to calculate for delta T equal to 10 minutes. So we write it as 10 times 60 because it must be in seconds always. Okay, so this is what we have. Okay, we have V, we have R, and we have delta T. You have many options for equations that you can choose to find the work done. When I looked at your equation sheet, then there's an equation that says work is equal to V squared delta T over R. Okay, and I think that this is the easiest equation to use, or the one with fewest steps. So if we do that, V squared now is 150 squared. Delta T is 10 times 60. And R is 242. If you put that into your calculator, you will find that the work done is a very big number. It's 55785.12 joules. Okay, 55,785.12 joules of work. So this now, how many marks was this for? It was for 5 marks, okay? So if you can write out all the information that's given to you like this, and then use, then look at your equation sheet for different options of equations, because you already know how to do it, but you're just trying to find the best equation to use. So you can do it like that. Okay, but I suppose if you had done it, I'm not sure, I'm just assuming that you might have, knowing that you've got V, R, and delta T, that you might have first calculated the power. Okay, so you could have done that as well. You could have said the average power is the V squared V RMS, but they told us that it's 150 over R. You could have done that, and then you would have gotten 150 squared over 242. I think that's 92.975 watts, because it's power. And then you know that power is equal to the work done over time. And then from there, we can calculate that the work is power multiplied by time. And that would have been 9. Oh, okay, let me just write it here. It would be 92.975 multiplied by 10 times 60. And you would get the same answer, 55,785.12 joules. The point I'm making is that you may have a different way of solving it. And all of them, there are many different equations that you could use that would give you the same answer. But it's worth it for you to look through your equations and see which one is fewer steps, because this is basically the same thing. Someone may also look at this and try to calculate the current I, and then from the current calculate power or whatever. Different methods, many options. This is my first choice, the one that I did here. but you can also do the other ones if you are happy with that, if it's familiar to you. Okay. Okay, do you have any questions?
I don't think we have any questions, so you can continue.
Thank you. Okay, so we made it to the last question.
Yeah.
Okay, so
Sorry,
here's question.
I just
Yes?
shared something. Sorry. I just shared something in the chats. Can everyone
Okay,
just
Sandila,
highlight?
can I just say something? Guys, listen, don't share anything on the chat, okay? So don't share your score on the chat. If you go to the link that I've put up, there's a register you sign. You have a place to record high school and all of your information. That information will remain with me for communication with you, but I don't want you to put any information directly on the chat.
Oh, okay. No, that's fine. Okay, that's fine. Sorry about that. Okay.
Okay, bye-bye.
Okay, thank you.
Okay, so we're looking at question 10. Okay, an experiment is conducted to investigate the relationship between the frequency of light incident on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. This experiment is conducted for 3 different metals. The graph below represents the results obtained. Okay, so as soon as we look at this, we know what section this is, and we're very happy because we like to calculate the work function and maximum kinetic energy. Yes? Okay, so the 3 metals are potassium, zinc, and platinum. On the x-axis, we have a frequency, and it's times 10 to the 15 hertz. On the y-axis, maximum kinetic energy in joules. Okay, so the first question is, okay, can you hear me?
I can hear you.
Okay, thank you. Okay, so 10.1, name the phenomenon on which this experiment is based. And we know what that is. So 10.1 is photoelectric effect. Okay. Photoelectric effect. So easy 1 mark. 10.2. Name the physical quantity represented by X on the graph. Okay, so if you look here, it's showing us the kinetic energy up to 0, and this is below that. And so we know that is the work function. Okay, oopsie. It's called the work function. And also, I should just tell you, because we should write properly. If you look at the graph, that is the work function of potassium. So it would be nice to write of potassium. Okay. Next question. Which one of the 3 metals needs incident light with the largest wavelength for the emission of electrons? Okay, give a reason for the answer. Okay, so 1 mark for which metal and 1 mark for the reason. Okay, so which one needs incident light with the largest wavelength? Okay, so when we're looking at it here, you can see potassium, zinc, and platinum. And if you look on the x-axis, it's showing us all the frequencies. Okay, so if you look here, you can see that potassium has the lowest threshold frequency. Okay, this is the, where it cuts the x-axis is the threshold frequency. So potassium has the lowest threshold frequency, so it will need the largest wavelength. Okay, so let's write that. The answer is which metal, and it's potassium. Give a reason. Because it has the lowest threshold frequency, or you can say it has the lowest work function. Okay, either one would be fine. Okay, 10.4, define the term work function in words. So work function in words. So you know what the work function is? It's the minimum energy required to emit a photoelectron from the surface of a metal. Okay, so 10.4. The work function is the minimum energy required to emit a photoelectron from the surface of a metal. Okay, let me just, okay, so it's for 2 marks, okay? Work function is the minimum energy required to emit a photoelectron from the surface of a metal. So you must put in all these important words like minimum energy and photoelectron emitting and surface of a metal. Okay. The next question. So for 10.5, they want us to calculate the work function of platinum. Okay, so if we look at the graph, we look at platinum and we can know what the threshold frequency is. It's exactly between 1.5 and 2, so it's 1.75. And remember that it's showing us here that it's times 10 to the 15 hertz. Okay, so the threshold frequency for platinum is 1.75. We're reading it off from the graph. So let's do 10.5.1. Okay, so the work function is equal to H F naught. And H is Planck's constant, which we will just get from your table of constants. 6.63 times 10 to the minus 34. And the threshold frequency, we read that off from the graph. 1.75 times 10 to the 15. Put that into your calculators and you should get 1.16 times 10 to the minus 18 joules. Okay, and so this is work function, W naught. So that is the work function of platinum. The next question, which is related to that, it says, calculate the frequency of the incident light that will emit electrons from the surface of platinum with the maximum velocity of 5.6 times 10 to the 5 meters per second. Okay, so they've got the maximum velocity. They want us to calculate the frequency of the incident light. Okay, so the equation that we use is that energy is equal to work function plus kinetic energy. Okay, and energy that is incident is HF is equal to work function plus, I'm just going to write it as kinetic energy again. I'm trying to find the frequency. So instead of substituting values, I like to leave it like this. So it's equal to work function plus kinetic energy divided by H. And when you have your equation like this, we can substitute the values. Okay, so what is the work function? We just calculated it here. 1.16 times 10 to the minus 18. So 1.16 times 10 to the minus 18. Okay, we just calculated it for platinum. What is the kinetic energy? So that is, and I'll write it here. Kinetic energy is a half mv squared. Okay, so for kinetic energy, it's going to be, oh, sorry, it's plus a half m. So what is m? M is the mass of an electron. Okay, and you can take that from your table of constants. It's 9.11 times 10 to the minus 31. And v squared, okay, now they told us what it is. They said it will have a maximum speed of 5.6 times 10 to the 5 squared. And we want to divide all of that by h. 6.63 times 10 to the minus 34. Okay, and if we put that into your calculator, you will find the frequency to be 1.97 times 10 to the 15. It's a frequency, so the unit is hertz. And that is the answer for the frequency of the incident light. Okay. And that is the last question.
Ashna,
Yes.
I have a question from a student. One of the students is asking, how do you interpret the work function graphically as well as the threshold frequency?
Oh, okay. So when you're looking at the graph here, they're showing us that this is the zero line here where the kinetic energy is. So the work function is the minimum energy that is required to emit the photoelectron from the surface. Okay, so let me just explain something here, or try to. So if that is the metal surface, and these are all the electrons that are in the metal, you have your incident light coming in, okay, that has some energy E. Then each metal has a different amount of energy here that is required to release this electron to bring it to the surface there. And the amount of energy that has to come in here to release it from inside there to bring it to the surface here, that is called the work function. Okay, so if you have energy which is equal to the work function, then the electron, the photoelectron, will just come from the from inside the metal onto the surface. If the energy that's coming in is larger than the work function, then this electron now will have energy to fly off. It will have some kind of velocity, or it will have some kinetic energy. So when we are looking at the graphs here, and where the graph cuts this axis for the energy equal to 0, that frequency is called the threshold frequency. Okay, I hope that explains it.
I'm sure that's fine.
Okay. Are there any other questions?
If you have questions, you can unmute your mic and speak.
Oh, I was supposed to do the one question on the direction. Oh yeah, okay. I'm gonna try to unmute. Okay, I want to just explain to you in this question here. Remember question 9 on the DC motor? They want to know in which direction will this coil turn. Okay, so let me just show you this. I'll try to show you this one here. I'm going to, so you can see the coil here now, and we can see the battery, the positive and negative terminals. I'm going to label the coil A, B, C, and D. Okay, and then also I'm going to show you on here the direction that the current is going to flow. So current flows from the positive terminal. So if we look here, the longer one, the current's going to flow there, here, and then it's going to flow from C to D across there, and then from A to B. And then it's going to come back here, okay, into the battery. So that is how we determine the direction in which the current's flowing in the coil. The other thing we need to know is what is the direction of the magnetic field. Okay, so I'm going to use the red pen. So you look at your magnet, the one pole is north and the other is south, and the field lines are always going to go from north to south. Okay, so that's the direction of the field lines. I don't want to mess up the drawing, so I'm going to just do that. Okay, so that's the direction of the magnetic field lines. So the red arrows showing you the magnetic field lines, and in blue, I've got the arrows showing you the direction in which the current is flowing. Because this is a DC motor, you're going to use the left-hand rule, okay? We usually use the right-hand rule. So if it was a generator, you would use the right hand. But because this is a DC motor, you're going to use Fleming's left-hand rule. And the way you do it is you take your left hand, you use your thumb, your forefinger, and your ring finger to do it. I'm going to unmute. I'm going to turn my video on now and try to show it to you. I'm in a different location, so let's just try. Okay, I want to just, before I do this, you're gonna have to be able to remember the picture. So you can see the field lines are going from north to south. And if you look from A to B, the current's coming towards me. Okay, so I will show you for A to B.
Shala, just a quick question.
Okay.
Sometimes that cameras and screens, they flip the image. They give you a mirror image with your hands. Is this going to affect the interpretation of the rule?
I don't know. It shouldn't.
I'm just asking.
I don't know. But it should be. Let's just try it and see. What do you think?
Okay, go for it. Go for it. Go for it.
Okay. Okay. Oh, that's what happened. Oh, okay. Okay, guys, I'm gonna try this. Yeah. Okay, so this is my left hand. Okay, and we're going to use these fingers. So your forefinger has to point in the direction of the magnetic field. Your ring finger or your middle finger is going to point in the direction that the current is flowing. Then your thumb will point in the direction of the force. So if you can look at the drawing that we have, the field is going from north to south in that direction, okay? And then from A to B, the current is flowing towards me. So my middle finger is pointing towards me. And then my thumb is pointing upwards, which means that from A to B, the force on that coil is going to be upwards. If you look at the other part of the circuit, where the current is now flowing, A, B, C, from C to D, then the forefinger still points from north to south, but the current is now flowing away from me. So I have to turn this left hand like that. So my forefinger is still pointing from north to south. The current is flowing towards you or away from me, and my thumb is pointing down, which means that the force on that segment is downwards. Okay, I'm gonna go back to my screen. Okay, can you hear me and see my screen now?
Yes.
Okay, so what I hope you could have seen was that for this section A to B, when I used the left hand, my thumb was pointing upwards, which means that the force was pushing up there. And when I had to turn my hand around for the current flowing from C to D, the force was down. So can you see if the coil's going up from A to B and it's going down on that side, it is spinning anti-clockwise. So that is how you get it. But it's basically using the left-hand rule because it's a DC motor. That is the part I wanted to explain. Okay. So that's it from my side.
Okay, Ashil, I had a question in the chat. Students want to know what we're going to be doing for the next session. So the next is scheduled for the 11th. I think that's the day before the paper, right?
Okay, I'm not sure when they're writing. From my side, I can prepare some other questions from past papers, something different from what we've already done. But ideally, if they could send us, they could email the questions that they'd like us to do or whatever, we can reply to those, or they let us know what they want us to do, which type of questions, so we can do what they want.
Okay, so students, I'm just going to put the email address up, which you probably already know from the pamphlet, but this is the physics chemistry mailbox, right? If you email your questions here, the questions will go to Mzwandile and Ursula, and so they will use that information to generate the next session. And we do have some time between today and the 11th, so maybe we could slot a few extra sessions in. The tutors, I mean, Ursula, do you think that's fine? Would you be able to?
Yeah, we could. Maybe we can chat off here and then you can let them know. We can.
Okay. We'll communicate to them through the website and through the emails.
Yes, and they can just let us know. Yeah, that would be fine. We can put in another
But in the meantime, you can send your questions to the email box, okay? Okay.
Yeah, I think if they send emails, we'll know just how much of interest there is.
Yeah.
Yeah, I think via the emails it will be much easier to track which question were they interested in.
And if there are lots of questions and we need another session, then I'm happy to do it.
Okay, so some students are asking about the June supplementary paper. Yeah, we'll just write that down and keep a note of it.
Okay. June sub. Is that this year's paper then? Hey?
This year's June sub, yeah.
Okay.
And they need more work on Newton's law.
Oh, okay.
I remember Newton's law is usually covered in grade 11. They don't cover it in grade 12. So I think maybe it makes sense they would want to revise that as well.
Okay, yes, if they let us know, then we can prepare.
Yeah, and look at it.
Per session.
Yep, just send your information to the email, send your request to the emails. Is anybody else with any other questions? Ashila, I was asked by some students to tell you that the sessions helped them a lot and they really appreciate what you've done.
Oh, I'm so happy. Thank you for that.
Okay, then if there's no more questions, we will close the session up. I'm going to play a short video on how you can apply to a university. And I'll still be on the chat, so if you want to leave any messages or any queries, I'll answer you while the video is playing. Thank you.
Part of the UKZN experience is the opportunity to be part of a community and to network with not only our world-renowned academics, but with future game changers and leaders. They do say that the extent of one's success can be attributed to those they rub shoulders with. Therefore, you must surround yourself with like-minded people. So, how do you become part of a community that is committed to your self-development? How do you become part of UKZN? First, you have to apply. All applications for undergraduate studies at UKZN are processed through the Central Applications Office, CAO. This is for both your course and student residence application. The application process is as follows. Step 1. Consult the CAO handbook. This handbook provides a list of all qualifications available at UKZN. Step 2. Have a look through the various courses offered and choose a program that interests you and for which you meet the minimum requirements. As one of the top 5 universities in the country, UKZN promotes academic excellence. So meeting the minimum requirements does not guarantee you a place to study. Step 3. Find the program code linked to your chosen qualification. This is the code you need to enter in your application form. Okay, let me show you something. You see, a code has 3 parts. Example, for BCom in accounting, the code is KN-P-BCN or KN-W-BCN. Crazy code, right? Well, basically, the KN stands for UKZN, the middle part stands for the campus of your choice, P for Pietermaritzburg, W for Westville. Then BCN stands for the actual course. Make sure to get these codes right. Step 4. Use this program code when completing your CAO form, which is available from the CAO website. Your application will be sent to UKZN. You can always check the status of your application using your CAO number, ID number, or passport number on this website, www.caocheck.ukzn.ac.za. For more information, visit www.cao.ac.za. It's that easy. Pay close attention to closing dates for qualifications. For example, MBCHB closes on the 30th of June, whilst other undergraduate programs close on the 30th of September. What are you waiting for? Apply now and shape your future today.
Okay, students, thank you for attending. I'm going to close the chat. If you need to ask any questions about academic stuff, you can email the email boxes. Also look at the pamphlet and the information posted on the website to see when the next sessions are. And good luck with your studies so far. Thank you for attending.